Hello, welcome. This is now question 7 for Edexcel's M1 June 2015 paper. So basically I've drawn this graph, what you're asked to draw for part A. Now I've obviously not drawn anything on it because we've got a bit of background to go through. So we're told to train, actually before I do that, the gradient of a speed at time graph is acceleration or obviously deceleration if it's a negative gradient. Now, the reason for that is we've obviously got this, I wrote this SUVAT equation for distance, which is initial speed times time plus a half times acceleration times time squared, and that is equal to the distance covered. Now, the reason this gradient is represented by acceleration, if we take out, say, from initial point, the initial speed is 0, which it would be just when you're not moving. So if we discount that, so therefore S is equal to a half AT squared. Made a bit of a mess of that. Just it is, speed over time is acceleration. So because acceleration is meters per second squared, so effectively that's irrelevant. Tried to explain that but it didn't go well. Anyway, so ignoring my colossal mistake, quite easy to ignore if slap you a £5 note. Anyway, so so basically this background is a train travels along a straight horizontal track between two stations, C, logical, A and B. The train starts from rest at A with a constant acceleration of 0.5 meters per second squared. Now you don't really need to pay attention to the units at this stage because we are just drawing the graph. All you need to focus on, it says constant acceleration. Now we know acceleration is gradient. Okay, so the constant gradient, just something like that. Put it fairly steep, but not too steep, until it reaches a speed of a given speed. It just says v meters per second, where v is greater than 50. Now that's not going to be relevant, as I said, just yet. The train then travels at this constant speed, hence no acceleration, so we're going to have a flat line for a bit. And then the train travels at this speed before a constant deceleration of 0.25, which is half the gradient of this. So you just need to put the gradient as a bit shallower on the right hand side. Okay, so what I would do here is I would split what we've got is shape. Then obviously we need to split this up into sections. Okay, so even though it's going from station A to B, so I'll just call this SA, Station A, and SB, Station B. Don't get confused with the support forces, because obviously we're not drawing a table, but I'm just assuming, your brain can comprehend that. What I'm going to do is split this up into 3 sections. So we've obviously got the first section where it's accelerating, and then a section where it's section where it's at a constant speed, and then third section where it's at a decelerating speed. So the first I'm just going to call this section 1, section 2, and section 3. Obviously you can actually just call that point A and point B. So section 1 is increasing in speed, and section 2 is constant, and then section 3 is at deceleration. Okay, so that's all you really needed to draw. Now mine isn't perfect, but obviously this has to be perfectly level. Okay, we're told the total time for the journey is 5 minutes. So obviously what I would do, because we're told in the speed is in meters per second and we're given in minutes, the first thing I would do is, okay, well the total time we're told is 5 minutes, so therefore obviously 60 seconds in a minute, so obviously that's 300 seconds, 5 times 60, so there's obviously 300 seconds from going from A to B, including deceleration and acceleration times. Okay, so find in terms of v the length of time in seconds for which the train is accelerating. Okay, so we need to break this down. As I said, I broke it down into sections. That's kind of skipped ahead of myself. So that was part A, drawing the graph. Okay, so it's quite a nice part A. This part B, as I said, we need to find in terms of v the length of time for which a train is accelerating. So obviously that's part A, or part 1, sorry. Now we need to go back to the figures. We were told there's an acceleration of 0.5 meters per second squared. So I break this down into, so B part 1, which is what this is, the acceleration, so it's accelerating if you've drawn this on your graph, you can put accelerating in section 1 only. Now they would only ever, at AS level or A level, whatever you're doing mechanics at, they would only ever ask you to work out things like this when you've got one section that is accelerating, one that is constant, and one that is decelerating. They would never ask you to work out V in terms of T or whatever for multiple sections like this, because it'd be too confusing. So this is as hard as it will get in this kind of context. So find in terms of the velocity, length of time in seconds with which the train is accelerated. So we're going to have to go back to our old friend, the SUVAT equations. Okay, so we know the acceleration is the gradient of 0.5 meters per second squared. So the acceleration, or A, if you want to put it as that, is 0.5 meters per second squared, or a half meters per second squared. Okay. Are we told anything else? No. So what we want is we want V in terms of T. So we want to find out what V is in terms of T. So we don't know what V and we don't know what T is. But we just need to put them, so if we did know one of them, we could work out the other. So if we knew T, we could work out the velocity and vice versa. So we need an equation that links velocity, acceleration and time together. And the only one that does that the easiest is V equals U plus AT. Now granted we don't have U, but because it accelerates from rest, therefore U is obviously 0. So we can just discount that. You could have put that in your initial thing of U equals 0 meters per second, and that might have made it a bit obvious that you had to choose this one. Now we want V in terms of T, and we know acceleration is 0.5 meters per second squared. So you just sub it into this equation. So V equals a half of T, or V equals T over 2. Either one of them are acceptable. Okay? And we want, find in terms of the length, sorry, why can't I say length? Find in terms of V, the length of time T. So we don't want it we don't want it as a subject of V, we want it in terms of V. So therefore we just times this equation by 2, so we get T is equal to 2V, and that's acceptable. Sorry, I did kind of confuse you, that was the official answer. But I got middle because I was skipping ahead of a few questions. Okay, so that's section 1, remember. We're going to use that later on. So, the next part says where it's decelerating, so it's actually skipped. So we're moving on to section 3 here. Okay, so where it's decelerating. Now, it said acceleration is the gradient, so therefore obviously deceleration is also the gradient when we've got a negative figure in terms of acceleration. So our acceleration or deceleration, so our acceleration is negative 0.25 meters per second squared, or deceleration is 0.25 meters per second squared. I would have put it as acceleration is negative because look, it makes a lot more sense when you're trying to think of SUVAT equations, because you don't necessarily think of ones that have got acceleration as deceleration. Okay, I just think of it as negative acceleration, but totally up to you. As I said, I think it's easier to spot the SUVAT equations with them. Okay, so as again, we need an equation that links acceleration. We obviously know the final speed is 0 because it comes to a stop. So obviously the final speed is 0. We don't know what the initial speed is because obviously we're going to have to find that out, because obviously any equation we put V into it's just going to get rid of it. So we need to assume V is equal to U, sort of thing, if that makes any sense. If it doesn't, please ignore me waffling. And obviously we need to know T in terms of V, but obviously, or some kind of speed. The only speed we have left is U, so obviously it's going to be T in terms of U. And as I said, we need to, when that links V, U, A and T, and obviously that's the equation we used before, so V equals U plus AT, subbing what we know. So obviously it's going to equal 0 equals U plus AT. Now we know what A is, U take 0.25 times T. So therefore, obviously, you could write that as take T on 4. Oh, excuse me, T on 4. So therefore, U equals T on 4. We want it in terms of a speed, one t is a subject, so time per cycle by 4, so t equals 4u, or 4v, whichever way you want to put it. Now that's positive, by the way, can't be negative time. So don't be put off, you need to rearrange it, okay? So hopefully that makes some kind of sense. Right. The next part, the reason they've asked, there's a reason they've skipped out part 2, by the way. Because obviously it's going to ask us about part 3 now. Alright, so the next part 3, asks us to find the length of the time which is moving with a constant speed. So the same thing, find t in terms of v. Now we know that t is 300 seconds. Now we can't, sorry, bit of background actually first. We can't use one of these equations because A, we don't know the final speed. Well, we know the final speed at the end of the first section. We could do v equals t on 2, and therefore we could say, oh well, then the whole speed of this is t on 2, and the initial speed of this is t on 2. But that'd get far too confusing, and it'd be wrong. Besides that small little point. So the thing that we need to consider, so we also can't use these equations because there's no acceleration, so obviously that get rid of at, and we just say, okay, well v equals u, and that's not in terms of t, so therefore we can't use these equations, and therefore there's no other equation that links v equals u, v, u, a and t together, because we don't know the distance, so we can't use the other equation that involves v, u and a. Okay, right, so hopefully that makes some kind of sense. So we know the total time is 300 seconds. We haven't yet used that. So obviously that should be kind of ringing alarm bells. We've got to use this at some stage. He wouldn't just tell us this for no reason. Right, let's start at part B. So we know the total time so far. So we know the total time spent in section 1. We know the total time spent in section 2. So the total time spent in section 1 was 2v. So the t was equal to 2v. That's what's gone so far. So with t1, so time in section 1 is 2v. Time in section 3 is equal to 4u, but as we said, u equals v before, so you could put t equals 4v. So this 4u, you could say that's 4v, by the way. Doesn't really matter, it's just a speed. So therefore that's the total time that's been so far. So the total time that's been so far is the time in section 1 plus the time in section 3. And if you add them together, so t1 plus t3, that's 6v. So the time spent in section 1 was 2v, and the time spent in section 3 was 4v. So therefore we've spent 6v time so far. We don't know what that means. We don't know what it means. It looks pretty good, so let's use it. Now we know the total time so far is 300 seconds. So let's come up with an equation. Okay, so 300 seconds is the total time that we spent in the whole system. And we've already spent 6v. Now you can clearly see section 2, even by my cruddy drawing, section 2 is a lot bigger than section 1 and section 3 put together. So therefore we have to put that first. So what we're saying is the time difference between the total time and the time spent in section 1 and 3 is the time spent in section 2. Basically, these 3 sections have to add up to 300 seconds. And we've already used 6v time. We don't know what that means, but that's just t in terms of v. So it's the area in section 2, or t2, take 6v is equal, plus 6v is equal to 300 seconds, because that's the time spent in section 2 and the time spent in the other 2 sections. So we want the time spent in section 2 alone. So we just rearrange this to get t2 as a subject. So t2 is equal to 300 take 6v. Okay? So that's the length of time in terms of v, which is what we want. Okay, so what I'm going to do, I'm not sure if I could fit this on actually. What I'm going to do is actually going to just rub all this off and put the time period spent in each section above the graph, because this next section requires a bit of working out, so I'm going to need a bit more space for this. it's becoming a regular habit. This if obviously the board's not big enough, even though it's, you know, if you put it up right, it's about over half the length of me. But you know. Anyway, so as I said, hopefully that makes some kind of sense. We're just going to move on to that was probably the hardest bit of the question. The next part is just using SUVAT equations and what we've understood already. So it's just taking this information and applying it to SUVAT equations is the next part of the question. So as I said, that was probably the hardest bit. So I'm just going to rub it off and we'll move to the next part. So welcome back. This is the last little bit of question 7. So what I've done here is we're told the total distance between A and B is 6.3 kilometres. Now we need to convert that into metres, not because we're being scientists, although they do that anyway. It's because we're given the velocity in metres per second, not kilometres per second. So obviously we need to translate that into metres, which 1 kilometre equals 1,000 metres, or 1 times 10 to the 3 metres. Okay, so what we need to do is break it down into individual sections, the distances, and then add all them up, and that will equal 6,300 metres. Okay, because we can't go straight from all these times, put them into some SUVAT equation, get a distance. We need to work out the distance covered at each section, during each section I should say. Okay, so the first section, we know the time, 2 times v. We know the acceleration is 0.5 meters per second squared, and we are starting from rest. And then obviously you could take v equals t over 2, but we'll gloss over that. Okay, so the equation I'm going to use for this, that links these together, is s equals ut plus a half at squared. Okay, now u is obviously 0, so that just means the distance is half at squared, and half times a, which we know is 0.5, so it's 0.5 is a half times the time squared, which is obviously 4v squared. 2 squared is v squared, obviously 2v all squared is 4v squared. So that means our distance is a half times 4v squared, which obviously gets us 4v squared over 4, which obviously just gets us v squared. The next distance, well, the speed is constant, so there's no acceleration, so obviously a is equal to 0. Now I'm not going to use the time as 300 take 6v, I'm just going to call it t. Okay, so we've got a time of t, and we want to know the distance, well, s equals vt, because the distance is speed over, distance is speed times time, so therefore s equals vt. Okay, so that's just the distance. Because the speed is constant and we've got a time period. Now I could put there, replace t with 300 take 6v, but I hope you can appreciate that would be a lot of work and simply can't bother. And you don't need it, to be honest. I do apologise. Third period, well, we've got a negative deceleration. A is equal to negative 0.25 meters per second, don't forget the negative. And our time is 4 times v, and we want to know the distance, and obviously the final velocity is 0. So the couple that we could use here, but I'm going to use the one that we used first off, so s equals ut plus a half at squared. Now we know the initial speed here was the final speed of this section, which was the final speed of the first section. That makes sense. And the final speed of the first section we said was v. So therefore the initial speed of before we start decelerating is v. So hopefully that makes sense. So s equals vt plus a half at squared. However, this is take 0.5 times 0.25, or it's plus a half times negative 0.25 meters per second squared, but just ends up being a negative anyway. Take half times a quarter times 4v all squared, which is obviously 16v squared. Okay, so therefore the distance of the final section is vt take 2v squared. So vt take 2v squared. Okay, so hopefully that made some kind of sense, how we broke it down into the individual distances. As I said, I'm more than happy to email you the mark scheme, but that's just a quick breakdown. So we've got our three distances here that we need to add up. So s equals v squared, s equals vt. So the first section, I'm going to call it s1, s2 and s3. So the total distance, so 6,300 metres is equal to s1, so the distance covered in section 1, plus the distance covered in section 2, plus the distance covered in section 3. The distance covered in section 1 we said was v squared, the distance covered in section 2 was vt, and the distance covered in section 3 was vt take 2v squared, so it's plus vt take 2v squared. Okay, so that equals 6,300 metres because that's the total distance of all three. So if we simplify this down, okay, so obviously v squared take 2v squared is obviously going to get us negative v squared plus 2vt. Just wondering if I've done something catastrophically wrong here. Probably because I'm not going off my model answers and I'm just going off my actual answers that I made a complete hash of. So I do apologise. Sorry, I do apologise. Oh wait, sorry. Yeah, so we know t is equal to 300 seconds, yes, because that's the total time. So we just input t is 300. 300. So 6,300 metres, or you can just leave that at 6,300 now, is equal to negative v squared take 2v times 300. So that obviously gets you positive 300v. So I think I made a bit of hash of that. Anyway, so is that, I was saying I've done that right. That's negative. Sorry, I think I've v squared. Sorry, one sec. Do apologise. So that should be 3v squared. So move it onto the right hand side, so therefore 3v squared take 300v plus 6,300 equals 0. Just a case of that's a quadratic equation, so therefore you get 3v, you take 3 out, it's become factor, so v squared take 100v plus 210 is equal to 0. So therefore factorise this v, so it's v and then v, and the two factors are negative 30 and 70. You could have used a quadratic equation if you wanted to. Now, as we are told, v has to be less than 50. Sorry, I should have mentioned that. So therefore, v is equal to 30. Okay, so sorry about making a little bit of an error. Hopefully you can see where we got negative, because that should be negative there. I think it should be negative over here as well. Do apologise. Alright, so as I said, hopefully made some kind of sense. I do apologise, I feel I messed that last little bit of question 7, but what can you do, eh? Alright, so hopefully that helps. If it doesn't, I'm more than happy to go over that again. But, you know, hopefully you've got it from the first time. Oh, sorry, yeah, you move that across and then that becomes positive, if that made any sense. Yeah. Alright, so there's no other questions for part 7. Question 7, parts of question 7. As you can tell, I'm quite knackered. So anyway, thanks for watching, and we'll see you in the next video. I'm going to go to bed.